This is Physics 2211, Lab 3, Black Hole. So this lab has two parts. For the purpose of the first part, we want to analyze the net force on a star by a black hole and then use that information to find the mass. For the second part, we want to find the initial velocity of a spaceship so it won't crash into a black hole or a planet while it can closely observe the black hole. Some important info to know is the momentum principle, from which we can derive that the net force is equal to change of momentum over change in time. The final velocity is equal to initial velocity plus net force divided by mass times the change in time, and also the final position is equal to initial position plus the average velocity times change in time. We also need to know that the net force is equal to the parallel component plus the perpendicular component of the net force, and that the force of gravity is equal to the gravitational constant times the mass of the first object times the mass of the second object divided by mass of the position vector squared times the unit vector of the position vector. So for our initial conditions, we had the gravitational constant set to 6.7 times 10 to the negative 11, the mass of the star times 2 times 10 to the 30th, and also the change in time, the time interval set as 1 day or 86,400 seconds. So for the actual coding part, right here, we calculate the initial velocity and the final velocity here. Then we use that initial velocity to calculate the initial momentum and then the final velocity to calculate the final momentum by the p equals mv. And then we calculate change of velocity, change of momentum here, and then the net force is just equal to the change of momentum over the change in time. And then over here we find the parallel component of the force, net force that we just got. And then right here we calculate the perpendicular part of the net force through F net equals F net parallel plus F net perpendicular. And then we use all that info to then we in the formula negative g times m1 m2 over magnitude of r squared times r hat. We just isolate the mass of the black hole on one side by using this formula, and then when we run this, you see that the masses fluctuate, but it stays around the same area. And then the arrows here represent the perpendicular and parallel force. As you can see here, the arrows were generally larger in this area, but that's because the force of gravity on the planet by the black hole was stronger here because it's closer. And then our results was the mass of the black hole is 1.16 times 10 to the 34th kilograms. And then we have the magnitude of the net force, the perpendicular component, and the parallel component here. So part two, our system is the spaceship and the surroundings will be the black hole and planet. We have our initial conditions here with the mass of the black hole coming from the previous part, and then the gravitational constant, the mass of the planet, and the mass of the ship. For the ship speed, we got this through trial and error. So this is our code. Right here, we're finding the positions the relative positions of the object, and then we use that to find the force between those objects. Once we got the forces, we can then plug it into Newton's second law, the momentum principle, where we get the position update and velocity update equations. As you can see, the ship, which is the purple line, never crashes into the black hole, nor does it crash into the planet, but it does get closer to the black hole. So these are results. And then some possible errors could be like the non-constant force from the part one, rounding errors, and it also assumes that gravity is the only force acting upon the system. So what does it all mean? How does the net force and its parallel and perpendicular components differ from rate of change of momentum and its parallel and perpendicular components? So for the rate of change of momentum, this assumes that we need two different time points and also two different velocity points. While in the case of the perpendicular and parallel components of net force, we don't, or net force in general, we don't necessarily need that. In this case, though, we assume that the net force is equivalent to the rate of change of momentum so that we can get the info we need. So what if what if the spaceship wanted to enter an orbit around the black hole? For this, again, through trial and error, we found that if you set the ship speed in the x direction as -2 times 10 to the fifth, that it would enter an orbit.